Hi everyone, and welcome back to Population Growth. In this section, we're going to really start to dig in and understand how populations grow and change. Let's get a little bit of background. Earth is about 4.5 billion years old. Multicellular biota, this means multicellular life, is about 600 million years old. Human beings, give or take 200,000 years. It really just depends when you start counting. Human population growth that grew into billions. This is in the last 200 years. So we want to say to ourselves, how are we measuring population growth? Factors that affect population. There's the pluses and then there's the minuses, or the coming ins and the going outs. So immigration. An object goes from one area and comes from one population into another. Natality. An object is born and thus joins the population at a given area. Mortality. An object that was part of a population dies. Emigration. An object that was part of a population moves into another population outside that initial area. So the going in, immigration and natality, the coming out, mortality and emigration. Now we can actually solve for this. So let's define our variables. B is natality or birth rate. D is mortality or death rate. And R is the rate of natural increase. Remember I told you there were going to be a lot of R's. This is not R species. This is R rate of natural increase. So how do we solve? Total births minus total deaths equals the R factor, or the rate of natural increase. Essentially, what you're looking at here is a relationship between how many organisms are born and how many organisms die. Now, in a healthy ecosystem, organisms will be born and die and be born and die up to this thing called carrying capacity. And carrying capacity varies greatly depending upon the environment. And so whatever is going on in the environment affects the carrying capacity of that environment. Remember back to the lab that you did, or the worksheet that you did, we had the water lilies and we had the water striders, and then we had a really harsh winter, and those water lilies died, or many of them died, and so the water striders also died. Their environment changed, thus less of them were able to survive. Population growth rate. In a field, there are 1,000 dandelions. Over a harsh winter in 2017, 400 die. What is the predicted R value for next year? Hopefully, in that moment, you thought, okay, so we had 1,000 dandelions, that's the B, minus the 400, that's the D, and that's going to equal our R value, which is 600. It's a long ideal spring in 2018. At the end of the growing season, there are 1,500 dandelions. What is the B value? Well, we know what the starting population is. It's going to be 600. What we don't know is going to be that middle value. And then we know that at the end of the season, there are going to be 1,500 dandelions. So if we do the math, 600 minus a negative 900 equals 1,500. Essentially, this is our predicted population for the next year, and this is our predicted start population for the next year. When it's bad, it's lower. When it's good, it's higher. Environmental factors affect how many organisms there are able to be in a given area. What does a negative death rate mean? Think about it for a moment. Negative death rate. It means that more individuals survived than died, and the population was not at carrying capacity. So this means that you end up with a higher population in the next year, and then the environment acts on them, and maybe you have a higher population the next year. But this will only continue to increase until you hit carrying capacity, and then it will naturally fluctuate in a small range after that. Our values mean something. And these are actually going to be a percentage of change, or a percent rate of change. And I want you to think logically. Basically, what this is saying is that there's going to be a 3.5 increase, or for every one individual that dies, 3.5 people are going to replace them. This is going to be a really rapid growth rate. This does not typically happen in developed nations unless there's been a major social or political upheaval. And as that country normalizes, sometimes you'll see a rapid growth rate. What kind of an upheaval am I talking about? Something like World War II, when, potentially entire villages were wiped out. And then when those people did come back together, got married, met back up with the spouse that they'd married before the war, they tended to have a lot of children, hence the baby boomer generation. And even then, we didn't hit a growth rate of 3.5. 1. A growth rate of 1 means one person dies, one person is born. One person dies, one person is born. This is a flat growth rate. This often happens a number right around 1 in developed nations. 0.6. For every person that dies, just over half a person is born. This means that the country is shrinking. So here's a little population chart that just gives you an idea about how in that last 200 years, there's really just been an enormous population boom. So you can see how the world has basically been going along. So let's just do the agricultural revolution from there. It just kind of slowly increases over time. Stone Age, Bronze Age, Iron Age, Middle Ages. And the amazing thing is that the Black Death actually kills so many people in Europe that it takes a sizable chunk out of the population whole. And look at that exponential growth. This little tiny section here mirrors what goes on in the last couple of 100 years. But that is only possible because there was a huge void in the environment that wanted to be filled, and people filled it with more people. Then we get to the Industrial Revolution. And after the Industrial Revolution, it's gangbusters. We can produce houses and produce jobs and produce food at a rate that can accommodate these exponentially larger next generations. And this is a little bit of an older one because we know that we're above 6 billion people right now, but I think you get the general idea. I left this human population video in. This is the one that we watched in class the other day. If you would like to watch it, it's there for you, just in case you needed it again. Where are you in all of this? There's a link for this. I will put the link into the lesson if you'd like to watch it. If you missed class, you can go and you can find out where you fit in to all of the population. Where were you born? Who came before you? Who came after you? But for the sake of this video, I'm going to just skip forward and allow you to do that activity independently. Exponential growth calculation. It's called the rule of 70. Please don't ask me what the 70 means. It's just the rule of 70, and that 70 is basically a mitigating factor, a holding factor that makes the rest of the equation work out. So calculating and predicting growth rates. With populations that are growing exponentially, we can use the rule of 70 to predict rates of growth and population doubling times. Assume that growth rate is a constant. This is an estimate only. So in other words, when you use this formula, it's going to give you an idea about what's going to go on in the future, assuming that nothing else changes. Now, of course, social changes and political changes and economic changes in a country can change this doubling time. But this is assuming that nothing is going to change and that the world is just going to progress forward. This gives you an idea about what's going to happen. So doubling time equals 70 divided by the percent growth rate, or percent growth rate equals 70 divided by doubling time. So let's take a look at a little bit of practice. Unfortunately, my answers have already come up, but that's okay. There's my problem. Doubling time equals 70 divided by that 2%, which means that the population of rabbits is going to double in 35 years. If the doubling time for a population is 7 years, what is the growth rate over this period? Growth rate equals 70 divided by 7, or a 10% growth rate. In the next video, we're going to talk about factors that limit a population. And those limiting factors are going to change how exponentially a population is able to grow.